Hi class, this is the video where we're going to talk a little more about scientific reasoning, and then we're going to go on and I'll just say a few words about what you might expect on exam 3. So first of all, one of the reasons I chose the Robinson is I really like his discussion of how we start looking at these things and where we could go wrong in terms of scientific reasoning. But let's just start with the most basic point here is what's called a statistical claim. A statistical claim is simply a numeric fact. And there's a couple of important realizations there. One, uh, if we don't, there's facts, and remember, we're in an argument class, and there's inferences from those facts. And obviously, the latter is what is important because that's how we use statistical claims. But also, depending on how those statistics are presented, it can be very easy for us to draw the wrong result. So think back last unit to generalizations and uh, where some of those go wrong. We're going to see some very similar points here. And again, I like Robinson's discussion of it, so I'm not going to beat you over the head by basically rereading it to you. But in general, we should watch for some of the same things we did before. Watch for agendas, who's presenting the statistics. Do they have interest besides truth? That's one way to be skeptical that Robinson doesn't say as much about. But then secondly, the kind of things we watch for involving statistical claims are things like scope and scale and things like that. And again, I'm not going to go through all of them, but these are general ways where people can manipulate with statistical data. And the best way to avoid that is to understand what the statistical claim being made is, what does it say, and if we're inferring beyond that, are we justified in that inference? And then, of course, there's also these big underlying assumptions about, well, again, the most basic argument is the inference to the best explanation. So we can talk about what explanations are there for those statistics. So the one example he gave is this seemingly dramatic increase in murders, but it's not murder rate. The murder rate is actually staying the same and going down because the best explanation for more murders is increase in population always equals increase in murders. So without going into each and every one of those, just make sure you're watching. Now, how do we start inferring from those statistical claims, though? The big issue and what we're really interested in is causation, right? We're doing induction, and so we want to know if there is some sort of causal relationship between whatever we're looking at. Well, do we have reason to think that there's an important cause we should worry about for the increase in murders? And so here it's important to understand the distinction between correlation and causation and what's being established and all of that. It's helpful to think of causes in a few ways. One, a complete versus partial cause. Whenever we're talking about statistics, we're almost always talking about partial causes. A complete cause just means when A happens and B happens. So decapitation causes death. By contrast, a partial cause is, say, a major contributor that you could have the cause without the effect. So chain smoking causes cancer is a partial cause. And so because we're interested in the partial causes, it's helpful here to break things down even further into the reliable causes and probabilistic causes. The smoking case is a probabilistic cause that, while it's still nowhere near a guarantee, by contrast, a reasonable cause is something that happens the vast majority of the time. And the rest of part 20 is going into kind of, well, when does correlation become causation? Robinson gives a somewhat simplified account of that. Interestingly enough, there's a really important study, and it's not a coincidence I've been using smoking and cancer as an example. When the FDA first basically figured out and claimed that smoking causes cancer, they had to talk about, well, when does correlation establish causation? That's an incredibly difficult task, by the way. And in this groundbreaking study, this isn't in the Robinson, by the way, they said that there's 5 kind of criteria that allow you to infer causation from correlation. The consistency of association, the strength of association, the specificity of association, the temporal relationship of association, and the coherence of the association. So that's kind of the big kids table if you want to actually talk, go beyond the Robinson to talk about how do we go from correlation to causation. Consistency, strength, specificity, temporal relationship, coherence of the association. So just to do one more example. Say I wanted to say something crazy like studying leads to better exam results. Now, obviously, this is a partial cause because there's people who study and don't do well on exams. There's people who do well on exams and don't study. So, can we say, in the usual sense of the term, that studying causes better exam grades? Well, when does correlation become causation? So consistency of the association means something like, well, we don't have people who study really hard and do a lot worse. That it's consistent with the data that studying is generally helpful. The strength of the association, well, is there a correlation between those who study and those who do well? The specificity of the association is, well, what are we talking about when we mean studying? Do we have things like people who study more and people who study less? Do we see that shifting as well? Do people do better on the exams that they studied for than the ones that they didn't? That would be the temporal relationship. This isn't a great example for temporal relationship. And lastly, the coherence. Can we make sense of why someone studying might lead to better exam scores? Hopefully all of that seems obvious to you, and that's why you study for exams, I hope. But all I wanted to emphasize is, notice there's something to this. We're just unpacking something you already know. You already know there's people who study for exams and still bomb them. You already know there's people who don't study for exams and do well on them. And yet you're perfectly willing to say that you're willing to use the word because, that the cause of me doing well on my exam is that I studied. And that I should study in the future if I want to do well. And so we are willing to give this causal relationship. And so being able to articulate why is actually very valuable for when we're not sure whether to assign that causal relationship or not. Now, there's more we can do, however, and in chapter 21, in addition to discussing correlations in a little more effect and their significant correlation that suggests causality, there's also these types of studies we could do. If we want to, if we're in the sciences, we could test hypotheses. And there's 2 types of studies, observational and experimental. In observational, we just decide, well, what data would we collect if we want to establish these kind of associations that I was just talking about? Well, you would get a whole bunch of test scores, and so observational is just collecting data that's already out there. So if you could find the data that talks about which ones they studied for and which ones they didn't, and their exam scores, etc., then you can do what's called an observational study, where you just look at the data and figure these things out. Actually, by lovely spouse does these things sometimes at the hospital. If we want to test a hypothesis about whether a certain thing is good for pregnant women, they have all this data collected from pregnant women, and they could just look at the relevant features and see if there's something there. By contrast, an experimental study is when you are instead setting out an experiment in which to collect the data, and that's when we need control groups and things like that. So when we want to actually determine if a correlation involves causation, we could think about what kind of experiment we would like to do. What's the strongest observational data we could see and check to see if it's there. But also remember negatives. Well, what kind of observational data would disprove it? Well, if people who didn't study did just as well as people who did study consistently, that would serve as a decisive refutation and saying that no, studying, it does not cause you to do better. I know that's all very fast, but A, the hard units were 1 and 2. B, again, I really like Robinson's discussion, and I don't want to just sit there and beat you over the head with it. So see what you can do with it. Let's talk about exam 3. So exam 3, we're looking at 2 major things. We are interested in, well, obviously what we talked about in terms of concepts and in terms of evaluation. For concepts, expect this one. We haven't had much of it before, but expect a lot of multiple choice. Just to ensure you have all the concepts that are on the review guide. In terms of evaluation, expect some cases like the last 3 questions on the previous exam, where here's a case, here's some data, what should you do with it and why, what inferences should you draw. And so just be prepared to do that, and you should do fine. Otherwise, we will see you in Unit 4.